So I'm going to just read the answer then, or question. The Puget Sound geoengineers did a good explanation of liquefying gas. So hopefully this one has more in-depth info on the process. Well, it's pretty high level. I guess, so I guess I can't like see a raise of hands, but I was wondering how many people also went to that one.
Yeah, let's get started here, and we can. I'll introduce some rules of the road here. So, hello everybody. Hello everybody. I am Mark. I am just helping facilitate, and then I'm going to mispronounce your last name because I'm always famous for this. But we have Mr. Weinken.
Winken. Yep.
Winken.
Close enough.
See, a little bit off. That's close. He's going to be presenting to you. Here, I'm going to stop share here. Hang on. And so just some rules of the road. There is a raise your hand function. It's in the bottom. So when you get asked a question for raise your hand, you can always do that. Also, a Q&A is where you're going to ask questions. The chat is probably turned off. So if you do need help, put it in the Q&A. I will be monitoring the Q&A for everyone here. So without further ado, I'm going to hand it over to you.
All right. Okay, can you see Northwest Natural on the screen?
Yes, sir.
And so just quick question. So is there a way to speak to the students or have them, like if I want to ask for feedback, or is it only communication through the chat?
They can put in things in the Q&A, and then they do have a raise their hand function. So if you see them on the right side.
Okay.
How about students? Raise your hand. Just everyone raise their hand. See what it looks like. Ah, there we go.
Oh, okay, cool. Okay, that's something.
All right. And I'm going to lower everyone's hands. All right, off you go.
All right. So, I am going to. Okay, I got a quick raise your hand question. How many people went to the Puget Sound LNG presentation? Raise your hand. Okay, not too much pressure then. Because I don't know what they covered. So this will be maybe a little different, maybe a little similar. But I'll just go ahead and start. So my name's Hunter Winken. I am a project engineer and project manager for Northwest Natural. And I manage projects at our 2 LNG plants along with some other peers. And what I'm going to do is just hit on some high-level information about Northwest Natural, explain a little bit about why we even have LNG, and what it is, how we make it, and then some of the engineering projects that we undergo. So starting off, Northwest Natural is about 160 years old, so it's about as old as the state of Oregon. It's one of the oldest companies in the state, and this little map on the right shows our area where we provide service, natural gas utility for everything in this area. Well, not everything, but most of that area. And I'm going to switch back over here. We have 2 LNG plants. One is in Portland and one is in Newport, Oregon. So Newport down on the coast, and Portland, Northwest Portland over toward St. John's kind of direction, Northwest Portland. And here's a photo of our Portland LNG site. This was built in 1966. It is actually one of the earliest LNG sites in the country. And at the time was pretty advanced, and Northwest Natural was fairly progressive in going this direction and implementing LNG at the time. And pretty far ahead of other operators. We then added another LNG plant in 1977, and this is in Newport, like I mentioned. It's a larger plant. It was newer, obviously, so it's a little more advanced. This facility was actually originally meant to import LNG, but that never came to fruition. I think there was an issue with getting ship traffic to the site. Nevertheless, it was built there, and we use it today. We use both the sites. And just a quick, what is LNG? So it's natural gas that is very condensed. That little picture, which I borrowed from PGE, so they may have, our Puget Sound Energy, so maybe they had the same one. Anyways, you can kind of get an idea that you take that beach ball there represents natural gas, like at its full size. So, if you let gas out of your stovetop and just let it sort of fill a space of air, that's what gas is normally. And then that little ping pong ball is what we condense it down to when we convert it to a liquid. And you've probably seen this kind of experiment before, but I just want to just get you a little feel for what this is and what it looks like. Here's an operator at Newport LNG, and he's just gonna show you how this is not as cold as liquid nitrogen. I think probably in your science class you may have had someone show you what liquid nitrogen does when you freeze stuff, but nevertheless, negative 260 degrees is still pretty cold, and you can quickly take a rose and freeze it and shatter it. We'll do a hot dog for funsies here. And so you know how when you boil water for to make tea, what's happening here is once you put that hot dog in the LNG, it's actually boiling. It just has a much lower boiling point than water, and so there you go. So why do we have natural gas or LNG as a utility? So Puget Sound Energy, they're providing natural gas to fuel vessels. And if you've paid attention to, sort of political news, there's been talk of LNG down at oh man, the name's escaping me, but down in Southern Oregon on the coast, and that's actually to export LNG. But so we're a utility, and I mean, just any guesses on why a utility has LNG? I don't know if this works. Can they message through?
So you guys, if you want to, let me see if I can turn this on for you. All right, I just turned on the chat for you guys. So if you want to put in some words in the chat, if you want to ask your question again.
Yeah, so why do you think this Northwest Natural has LNG sites? Any guesses? Thoughts? Okay, no thoughts. Well, so think about what happened in Texas recently.
I think we have some
Oh,
coming in. I think they were typing.
oh,
There you
okay.
go. Do you see the chat?
Yeah. This is great. Energy production. Places have more LNG than other places. The power companies, good place to harvest. Yeah, so kind of all of the above. The main reason is if you look at where we are, and I could have did the whole country, but if you look at where we are, over here, we are at the end of the straw, so to speak. So all the natural gas comes from up in Canada or over toward the Rockies. And with regards to coming from Canada, we're the last guy on the line. And then from the Rockies, same story. There's a little less demand on that line. Well, I guess maybe not. But so the reason we have LNG is a backup. So you can provide energy production like you're saying, Catherine, regardless of what's going on upstream. And so we also have underground storage. And LNG has the ability to provide an immense amount of natural gas very, very, very quickly. So if for some reason we lost all these pipelines or there was an intermittent issue, LNG can be vaporized very, very quickly, so we don't end up with blackouts or brownouts like exactly to prevent what just happened in Texas. So we have a very reliable system for the customers. And we actually had an example of this recently. This is a supply and demand sort of chart. And up in Canada, a pipeline ruptured. And immediately all this, and this was in the middle of winter, so immediately all the gas supply for British Columbia, Vancouver, for Seattle was instantly cut off and dramatically diminished to those areas. And in Vancouver, they had sort of emergency communication go out to the general public to turn down your heat, don't use your heat, use as little as possible. In Seattle, they have some reserves like we do, not quite as much, and they started pulling on those reserves. And here at Northwest Natural, we were able to instantly, like within hours, turn on our LNG plants and also turn on underground storage to provide that to the system. And you guys as customers never even got a notice to try and minimize your heat or anything like that. And this blue is the amount of gas that normally is coming from Canada, and then it just literally went down to zero. So this gap is what we filled from our storage, and by doing that, we actually let pressure off of Seattle, which was allowed the Rockies gas to make it all the way to Seattle without us sort of pulling from that line, and in helping our peers in other areas. So that's kind of one reason why. And I didn't realize this had all these things moving around. And the other thing is so it's not just the heat, but for your natural gas or your natural gas fireplace or for cooking, but it's for electricity. In the state of Oregon, about 30% of electricity is coming from natural gas, and that's because it's something that's easy to turn on and off. Historically, we had all, you know, maybe not all, but a lot of coal that was just a big piece of equipment running all the time, generating electricity. And now we're sort of allowing the demand to ebb and flow based on wind and solar and hydroelectricity. And then we just ramp up and ramp down the natural gas to fill a gap. And you know, as a whole, we end up producing a lot less emissions. And in the state of Oregon, I think they've closed any last coal plant at this point. So I don't think a lot of people realize it, but in Oregon, like I said, 30% of power, electricity is coming from natural gas. So that's why it's important. And so how do you make LNG? So one of the questions earlier, I think wanted a little more detail than maybe what I'm going to get into. However, I can dive into all the detail in the world at the end if we have time, and I'm happy to do so. But at a high level, we've got, it seems simpler when I first drew it. Anyways, at a high level, we take gas, comes in, and we go through a pre-treatment process. Oh, do I get a Q&A? Let me find the right button. Oh, did I miss that question? Oh, for what job? For my job?
I'm assuming.
Well, I'm a mechanical engineer. I went to Washington State University and learned engineering, and then went into consulting and learned how to build all this stuff. And then, so you need the technical skills in engineering, and then you need a lot of general engineering skills, which I'm going to show you in a minute. So hold that thought. Outside of engineering, which I didn't plan to talk about, but big area outside of engineering is communication, writing well, speaking, putting presentations together. That's very important. And if you get opportunities in school to practice that, I highly recommend it. So that's my quickie on it. So the process, making LNG, the gas comes in off a pipeline around 400 psig. I guess I don't know how to quantify that for you simply, but it's coming off a pipeline, and then we do two things. We clean the gas through a pretreatment system, and then we liquefy the gas, bringing it down to negative 260 degrees, as cold as you saw a second ago. And so, question, what is it you think we're doing to treat the gas, clean the gas? Why do you think we do that before we lower it down to negative 260 degrees? So if you can chat still, if it's allowed, I'd like to see some guessing. While you ponder, I'm gonna bring up a little view here. All right. Oh, the question was, so when we make, let me think how to frame the question clear. So ultimately, LNG is this liquid at negative 260 degrees. And then before that, it's gas. And we need to clean the gas and remove certain components before we go down to negative 260 degrees. Why do you think we're doing that? What do you think we're removing? Why do we need to change the gas before we liquefy it. Okay, so let me scroll up to no discrepancies in it, kind of, yeah. Is easier to treat as a gas than a liquid. Yeah, that's kind of true. Some of the things could be in the gas, causing it to potentially harden some particles in the, exactly, Mackenzie. It's still going to be flammable. Oh, I didn't show that video. Yeah, and particles that we want to get out of there. So I think, Mackenzie, you were the closest. The main thing we want to remove, okay, and so by the way, we're over at a corner of the facility. I got a scan. Unfortunately, my contractor didn't get me the entire plant for you guys. But this, can you see the little hands? Can you just nod? I forgot your name. Anyways, so gas comes in and yeah, so we want to remove things. So we're going down to negative 260 degrees. So we want to remove whatever's going to not be a liquid. And so that would be water is obviously going to turn into a solid at 32F, and CO2 is another contaminant that's often in natural gas, particularly if it's coming from the Rockies. And CO2 wants to, I think, turn into a solid at negative 150. You know, like when you buy dry ice in the at Freddy's or whoever your grocery store is. So we want to get those items out, because if we try and turn it into a liquid with water and CO2 in there, the system can't run. It freezes up. All those particles get stuck all over our exchangers. And furthermore, this whole huge tank over here, they all pile up in the bottom of the tank because everything in here is negative 260 degrees. So if there's water and CO2 in there, it sits in there forever. So we want to try and get all that junk out of there. And how we do it is we got two processes. We got these exchangers on the left and these vessels on the right. And the first ones are used to remove water. And how it works, if you've ever seen, well, I'm sure you've seen it. You know, if you got a shoe box and you get the little packet and it says like, poison, do not eat, that's got desiccant in it. That's got these little balls in it. And they put it in there to pick up moisture so your shoes are fresh and clean when you get them, and they don't have, you know, and so it keeps the humidity down in that little box. Well, these vessels, and that's called emulsive, these vessels are completely full of that stuff that you find in that little packet, 30, 40 feet tall. And each of those little balls, these little ceramic balls, are meant to pick up the water or the CO2, and they're specially formulated so those CO2 molecules fit just right in the little nooks and cranny of that ball and gets caught. And so as gas flows in, this gets filled with CO2, and then clean gas flows out, and then it goes into the next vessel, and then that gets filled with water, and then that goes out, and then you got clean gas, and it goes over to the liquefier. Okay, so now one more question. If you want to answer, I'll pause a second. How do you think we get the CO2 and the water out of these vessels once it's all full? We got CO2 in one, we got water in one, clean it out of the gas. How do we get that stuff out of there now? Any ideas? Because we can't just keep filling it indefinitely, right? Okay, Mackenzie, you did pretty good. What do you think? Right on. Yeah, well, we're going to release it, but how do we get it out of there? So it's stuck in there. And the gas came in around 70 degrees. It got caught in all those little balls. Gas left, but left behind the CO2 in the water. Okay, 5 seconds. Oh, I like what you're thinking. Not quite. So Mackenzie said, clean the water or recycle it. There's actually another process that does that. Oh, evaporation. There's another process that does that. Okay, boy, you guys are, I guess I could have showed you actually some alternate designs for LNG plants. Our LNG plant, with the type of products we have, so there actually is another design that uses CO2 and does let it evaporate, and it creates more emissions, so we don't do that, but there is a whole nother design that catches it and lets it separate out like that. So that's a good guess by Olivia, and similar concept by Catherine. And Mackenzie, there's actually a separate process that catches water in a solution of gas and then peels it out. But that's not what we have. Close. Amazing guesses. So how this works is this vessel, I'll just show you. I'll just zoom over here. So we've got this burner over here. And I realize I'm at 25 minutes if someone's worrying about time. This thing you see over here, it heats up hot oil to 600 degrees. That hot oil goes over here to some heat exchangers. And then we take gas, run it through the heat exchanger. The gas thing goes up to 100 or 600 degrees. And then we take that gas and we run it through one of those vessels once it's full. And then those little beads release the CO2 and the water. It all gets released. It's flowing out of there. And then we actually use that CO2 and water that's now being carried with natural gas, and we burn it in a turbine on site that then uses all that energy, exact same technology that they use to make electricity, but we use all that energy to run a liquefier, which I wish I had the scan from the contractor, but so we heat up the gas, runs it through these vessels, everything gets released, we burn the gas, creating not electricity in our case, but compression, which I'll explain what that's for in a second. And after we do that, running the gas through these vessels hot, we then cool it down and they're ready to go, ready to absorb more CO2 and more water and repeat the process. And that's why we got two. We can have one regenerating and we can have one absorbing. And we have three of these other guys for CO2 because we have 3 steps: absorbing, regenerating, and cooling. Okay, that was fun. Maybe fun for me, I don't. This is what the process flow diagram looks like. Don't know that I really want to get into it too much, but this is where that gas flows in. This green box is where all those vessels were. That some really good guesses on how that worked, quite impressive. And then the gas leaves all this rigmarole, flows over here, and it goes through some heat exchangers. Don't really have a good way to show you this because it's like 30 feet tall, can't exactly take a photo of it. But these little squares here, they're like a radiator, same kind of construction as the radiator on a car. That aluminum thin material with passes going through it. So the gas goes in one side and gas goes in another side, and it heats and exchanges and heats and exchanges, and eventually comes out at negative 260 degrees and goes in the tank. That compression I mentioned is going on over here. And so all that waste from all this stuff is going over here. It's running a turbine, which then compresses refrigerant and creates a cooling effect, just like the AC in your house, if you have AC in your house or your car. So that's all I had for the process, which, Olivia, hopefully that's not too much of a bummer for you. But hopefully it's better than Puget Sound. So engineering. So let's do quick hands. Who's here because they may want to go into engineering? Oh, right on. Okay, what discipline? If you want to jot it in there, and I'll let you know if your discipline of engineering you're interested in, and let you know how it fits in here. Okay, good point. Hard to pick. Yes, I'm a mechanical engineer, so obviously that's pretty good. So I'm gonna flip through some quick projects and just to give you a flavor for what it takes in these plants to construct them, or in my case, keep them up to date. And it's basically all the disciplines. And starting out with civil engineering, this is at our Portland facility. And what they're doing is the facility that the LNG plant was built on was actually built on a foundation that was on ground that is contaminated because of previous industrial activity there. And what happens is when it rains, the rain pools in this containment, and the containment's there in case the LNG tank fails for some reason. It will catch everything from the LNG tank. But as a result of that historical environmental pollution, whenever we have rain, it would get contaminated by what's in the ground. And so we did a $5 million project and went in and glued plastic liner down, multiple layers, and then refilled and graveled over the top of it. So when the rain falls into this impoundment, it's clean. There's no contamination in it. It can be treated minimally and released. So that's a civil engineering project that had to figure out how to keep enough weight on this liner so it doesn't float in the event there is a flood in the Columbia River or Willamette River that's on the far side of the screen here. I'm going to just show you real quick. Oh, this is too zoomed in. Well, over here is the Willamette, and the bottom of this impoundment is actually below the floodwater line for the Willamette. So there's a potential where that turns into a bathtub and wants to float up. So we had to get just the right gravel and rock on it so it's dense enough to hold it down in the event it wants to float up like a waterbed or something. So how am I on time? When's the normal wrap up? Do you know?
It was scheduled for an hour on our side, so right now we're about 35 minutes in.
Okay, they told me to keep it to 20 minutes or something before, so okay. I don't. I'm failing at that, but I won't take an hour.
How about this? Everyone who's listening in, raise your hand if you have 15 more minutes at least. You'll have an audience of 3 in 15 minutes.
Okay. I'll punch through. So geotechnical, so this is the study of the rock and what the ground's made out of. This is a project at Newport where we needed to put new equipment in, and the ground there is sand. So over time, we've engineering-wise have to build things to the current seismic code, which is meant for the big one, the big earthquake. And now that amount of energy in an earthquake would actually cause all the ground underneath the site to slide away. So if there was an earthquake that met that design, the soil would actually liquefy and turn into little bubble or balls and slide away. So we had, our geotech came up with one of their solutions is to put driven piles down to concrete, or excuse me, bedrock, to hold up the new equipment. So that's a geotechnical project example. Mechanical engineering, we have projects that include a lot of piping, and piping can get very complicated, particularly when it's at hundreds and hundreds of degrees. And here's another photo of, in this case, we put in new glycol piping. All this glycol piping runs all the equipment to keep it cool by using heat exchangers that are outside and run air through them. So just the normal air cools the glycol, kind of like with the radiator on your car, and then keeps all these pieces of rotating equipment happy. Electrical engineering, you've got all sorts of power users on site, and this was a recent project we did which provides emergency backup power generation, so we can run the critical equipment on site, and it uses natural gas, so we have like an infinite supply. And I think no matter what discipline in engineering you go into, you have to go into projects with sort of a safety of the guys who are building these things, and always keep that in your mind for how to construct it and how to operate it long term. And this is an example where we all get together and we talk about what we're going to do before we pick up a several ton piece of equipment and fly it around on a crane, just to make sure we're safe. And that's it that I had. So, tengo preguntas, questions?
I think Mackenzie's out of questions, but anyone else have any questions? Please type or put in the Q&A.
Okay.
Yeah, I never know if we have a slow typer or not. Ah, something just came in the Q&A. Where does the gas come from?
So, the gas comes from two places. Up in Canada, there is extraction going on, has been for a long, long time. Up in Alberta, Northwest Alberta, looks like it goes all the way up into the Northern Territory, but I think primarily it's coming from Alberta. And that's a very old line that has a lot of supply. And then additionally, I kind of cut it off, but over here to the right, the Rockies, Colorado, I think even further over is a lot of the other production. And so that's where it's coming from. Otherwise, there's no production in Oregon, Washington, maybe a smidge in Idaho, maybe a little bit in Montana, but most of it's coming from quite a ways away. Now I was going to show another.
Any other questions?
My pleasure.
Well, thank you very much. Appreciate your time. Thank you, students. And we will have a great evening. So thank you.
All right. Thank you, sir.
Everybody.